Let's look at some examples of actually solving separable differential equations. Now, again, we have three steps: separate, integrate, solve. So the first thing I want to do is get all the y's on the left-hand side and all the x's on the right-hand side. Easy first step is multiply both sides by dx. That way, dx divided by dx divides out to 1. And then I can divide both sides by cosine squared y. Okay, now I'm going to rewrite that a little less messy, and I have dy over cosine squared y equals 4x cubed dx. Now, I'm not entirely happy with the left-hand side because I look at that and I think, I don't know what the antiderivative of 1 over cosine squared is, until I realize that I do know that 1 over cosine squared is secant squared. So I'm going to rewrite secant squared y dy equals 4x cubed dx. Everything's separated and everything looks pretty easy to integrate. So we have separated, now we're integrating, and we know, of course, that the antiderivative of secant squared is tangent. So we have tangent of y equals, and we know also that the antiderivative of 4x cubed is just x to the 4th. But we've not finished because we know that we need to add a plus c. We need to add our constant of integration. I'll remind you that we could add a c to both sides and call one c1 and call the other one c2, but then I could move c1 from the left-hand side to the right-hand side and combine the two constants together and just make one big new constant that's called c. And usually we don't write out all that step, we just say this is our family of solutions to this differential equation. Without an initial condition, we can't go any further with this. So let's look at another one. This one looks a little more complicated. We have dy dx equals e to the x plus y squared over 2y. Now, very often, addition is a bad sign when we're trying to solve these things, when we're trying to separate these things. So before I try to separate, I'm going to try to change that addition to a multiplication if I can. And of course I know exponents that are added together can be changed to multiplication with the same base for the exponent. So we know that e to the x times e to the y squared is the same thing as e to the x plus y squared. Usually, a lot of times we're working the opposite direction of that, but in this case it helps us out to do this in this direction. And then we still have 2y in the denominator here. Now I'm going to do my separation. It's pretty easy. I'm going to multiply both sides by 2y over e to the y squared. And I'm going to also multiply both sides by dx. 2y over e to the y squared. And then I can just see that the dx will divide out to 1 there. And over here, this goes away, and this goes away, and this goes away. And I'm left with this separated differential equation, which is 2y over e to the y squared equals, dy, and this is a 2, it's a little sloppy, sorry about that, equals e to the x dx. Okay, now I am ready to start my integration step, so I'm going to do an integral. So we separated, now we integrate. And I notice over here on the left it looks like I may need to use a u substitution. So I'm going to use u equals y squared. and then I'm going to get du equals 2y dy. And that's nice because that's what we have in our numerator over there on the left-hand side. So I'm going to rewrite this whole integration step as the integral of e to the negative u. Since I want to pull that out of the denominator, I'm going to call it negative y squared, which means negative u du. And that's going to equal the antiderivative of e to the x dx. Now we can look at this and we know that the antiderivative of e to the negative u is negative e to the negative u, because we need that extra negative because we get, if we tried to take the derivative of e to the u, we would just get e to the u. If we tried to take the derivative of e to the negative u, we would get negative e to the negative u, so we have to add on another negative so that we get our sign correct. And then negative e to the negative u, and the right-hand side is really easy. That's e to the x plus c. Okay. Now I'm going to copy this to a new page. So we've got negative e to the negative u equals e to the x plus c. So negative e to the negative u equals e to the x plus c. Now we may want to go ahead at this point and plug u back in. So remember, u was y squared. E to the x plus c. So now at this point I'm going to just solve for y, so I'm going to multiply both sides by -1 so that I can get rid of the negative sign out front. So now I have e to the negative y squared equals negative e to the x plus c. I want to get y down out of that e, so I'm going to take the natural log of both sides, and that gives me negative y squared equals the natural log of negative e to the x plus c. There's nothing we can do to simplify that natural log, it just has to all stay together. One more time, I'm going to multiply both sides by -1 to get rid of that negative in front of the y. And I'm going to get y squared equals the natural log of the negative natural log of negative e to the x plus c. And finally, I would need to take the square root of that, and I'm going to have to say y equals positive or negative square root of negative natural log of negative e to the x plus c. Now that's our general family of solutions. We can't go any further without initial conditions, but our initial conditions would help us out with two things. First of all, initial conditions would let us solve for c. And initial conditions also would give us an x and a y, and then we would know if x is positive, that we would just get rid of the negative part of that, and if our y was positive, we'd get rid of the negative part. If our y was negative, we'd get rid of the positive part. So that's our general solution to this differential equation. All right, let's look at one more. Okay. And once again, this one starts out with some addition on the right-hand side, which can spell trouble when we're trying to separate. But this one's not too bad because I noticed that everything on the right-hand side has a y involved. So I'm going to say y, factor that y out, and I'm going to have just x plus 2. And that's going to make my life a little easier because now I just need to multiply by dx and divide by y, and I get dy over y equals x plus 2 dx. And this one's a little less complicated actually than the last one. We've just separated, then we integrate, and remember the antiderivative of 1 over y is natural log of absolute value of y. and that's going to equal the antiderivative of x plus 2 will be x squared over 2 plus 2x plus c. At this point we would go ahead and raise e to the power of both sides so we can eliminate that natural log, and we're going to get absolute value of y equals e to the x squared over 2 plus 2x plus, and actually I'm going to go back and call this C1 because we're going to do some of that magic we do with combining constants and say, well, I can split this up into e to the x squared over 2 plus 2x times, and I'm going to go ahead and say I could make this, if I made this positive or negative, then I could forget about the absolute value signs, and I'm going to say positive or negative e to the c1, but then I'm going to say all of this can just be wrapped up into one constant, and so altogether I'm going to try to, I guess I'll have to make a new page here, so I would say that we wrap this all up, we call it C, and so we end up with y equals C times e to the x squared over 2 plus 2x. So let me just write that on here. So y equals actually let's put the c first. So y equals c times e to the x squared over 2 plus 2x. And that's our family of solutions to the differential equation. And let's go ahead and say, what if we had the initial conditions on this one? And so let's say we knew that this that the particular solution goes through the point 0, 5. Well, at that point we can plug in 0 for x, and we can say, and 5 for y, and we can say 5 equals c times e to the 0 squared over 2 plus 2 times 0. Well, that's nice. This is all, of course, 0, and we know that e to the 0 power is 1, which is just c. So c is going to be 5, and we can come up with a particular solution to this equation that y equals 5e to the x squared over 2 plus 2x. Now we can also see very easily if that had been 0, negative 5, then we would have had a negative 5 here, and we would end up with a negative 5 here, and that's what we say when we say that the constant can help us take care of the absolute value a lot of times. Right, and those are just a few examples of solving differential equations. Okay, I just realized as I watched through this that I made a couple of mistakes along the way, and there's not a good way for me to go back and fix that, but I'm going to try to go back here, and I noticed that I did not actually finish this because I don't have what y equals on this first one, but that's one easy step. Let's just go back and we can come up with y equals the inverse tangent of x to the 4th plus c. And that's really all we can do with that one. I just didn't do that one last step. And then let me fix one more thing as we were solving this equation, when I multiplied by -1 here up at the top. I did not change this to a minus c, which I should have, although it doesn't technically matter because since we don't know what c is, the signs would all work out once we plugged in any initial conditions. But let me just fix that and say that should be minus, minus, and finally minus. So I apologize for that. That's the best I can do to fix this without re-recording the whole video, which I would prefer not to do. So sorry about that. Hope these help.